Hi, this is Mopin, and this is probably the last lecture of Condensed Matter 2 Introduction to Green Functions method, and today I'm going to talk about Majorana fermions and what are they. I'm going to have some introduction about them, and I'm going to talk about the bound states and the bound state engineering using green function. This is for the course Condensed Matter, as I've said, of spring 2020. So yeah, let's start. So today I'm not going to talk about detailed historic events behind the Majorana operators and how they were actually defined throughout the history by Majorana, but I'm going to have some simple intuition for these Majorana operators and how we can actually see them. So you're all familiar with these creation and annihilation operators F, dagger, and F. In condensed matter it is usually denoted as C, dagger, C. Doesn't matter, but both of them are actually two operators that creates or annihilates a normal fermion. And so these fermions are actually called a complex fermions because they're actually answers of the complex equation of the Dirac equation. So if you think of them as a complex Majorana, you can somehow write them as two parts of imaginary and real parts, and these imaginary and real parts are called the Majorana operators or the Majorana fermions. And these two actually acts as a normal, somehow some kind of normalization, and the F dagger would look like this. So yeah, and that's the picture you can have for these Majorana operators and Majorana particles, which both of them creates one normal complex fermion. So we all know these complex fermions do possess this anti-commutation relation, these two lines. This line is for anti-commutation of two creation operators, and this is for two annihilation operators, and you know they always do anti-commute. And for two different annihilation and creation operators, they do anti-commutes like this. Their anti-commutation is actually equal to the delta function, to the delta of ij. And for the real Majorana, if you go back and replace what we've actually defined in the at top of here, you will end up with something like this. So their anti-commutation will be equal to 2 times the delta of I and j. So for mathematicians and for physicists, this was very well known way beforehand as the Clifford algebra. So we can say that the Majorana fermions do possess the Clifford algebra, and the Clifford algebra has some interesting characteristics, and we can actually see it from this simple anti-commutation. If you go ahead and do the anti-commutation for the two states with the same I, you will end up gamma I squared plus gamma I squared is equal to 2, because delta I is equal to 1. So 2 gamma I squared is equal to 2, and gamma I squared is 1. So basically doing gamma twice is the same as doing the identity matrix. So doing it twice is actually doing it no time. And actually you can check that. It will give you gamma dagger is equal to gamma. So basically these gammas are Hermitian, and the creation and annihilation are the same thing. So from now on we're not going to denote the creation and annihilation, and we only use these gammas instead. So the gamma matrices, or the Dirac matrices, are well known to physicists, and it can be created by many representations. But one of the representation is to write them like this. So what we have here is that imagine you have the number of gammas, and you can actually create your gammas using this formula, and in here I stands for identity matrix, and sigma 1, sigma 2, and sigma 3 are the three Pauli matrices. So, and the pattern is like sigma 1, sigma 2, sigma 3, 3, 3, 3, 3, like that. I, 1, 2, 3, 3, 3, and then 4 I's, 1, 2, 3, and etc. So depends on the dimension of your space, on the number of gamma matrices you have, you can actually create these, and this sign is actually for the Kronecker multiplication, or the after multiplication that you're all familiar with. So as an example, let's look at it in 4 dimensions, or if you have 4 gamma matrices, this picture you can see that, like gamma 1, gamma 2, gamma 3, and gamma 4, or you can actually think of it as 2 complex fermions. So if you actually form them, you will end up with these 4 matrices, gamma 0, gamma 1, gamma 2, and gamma 3, and you can actually go ahead and check that they have this Clifford algebra identity of anti-commutation, and yeah, so that's one of the representation. You can have any matrices that you can create out of these that has this important relation. You can actually represent them as the Majorana fermions. So let's have some notes before going ahead. So yeah, right now we defined gamma and gamma dagger, or gamma 1 and gamma 2 as the 2 real and imaginary part of the complex fermions. And it is important to note that the notion of creation and annihilation operators as operators of increasing the number of Majorana fermions are not useful anymore. What do I mean? I mean, like, for complex fermions, we define some operator called n, which, when you acted it on your eigenstates of your Hamiltonian, you would end up getting some eigenvalue of n, small n, which represented the number of your fermions. And as you know, this f dagger increased the number to n, from n to n plus 1, and this f decreased it for 1. So that's why we call these creation and annihilation operator, because they basically increase the number of fermions. But the thing is that if you want to go ahead and create the same operator in the gamma matrices, well, as you know, the gamma dagger is the same as gamma, and gamma squared is the same as 1. We'll end up with the identity value. So, and you can check many other options that you have, but the thing is that the notion of the number of Majoranas are not actually useful in here anymore. So we're not going to talk about the number of Majoranas, but the number of complex normal fermions. So that's why we don't think of them as creation or annihilation operators. Some people always wonder why the creation and annihilation operators are the same, but yeah. Okay, until now we've been talking about these redefining of our normal complex operators in the term of Majorana operators, but how can this be useful? It all seems like a simple mathematical game. Well, it all becomes useful if we talk about a certain type of system, and the system is called the Kitaev chain. So the Kitaev chain, which is introduced by, of course, Kitaev, it was a chain of many Majoranas, like the picture, as you can see. These Majoranas are actually inside a superconductor, on the superconductor, and their Hamiltonian would be something like this. So what is this Hamiltonian? You are probably familiar with this kind of Hamiltonian, which in here, omega is the hopping amplitude. So this is the normal hopping term from J to J plus 1. This is the chemical potential, this is the on-site energy, and this is actually the superconducting gap, or the Cooper pair, as you might know. These are the term because of superconductivity. So this is the normal chain in superconductivity, inside a superconductor, so in here we write Hamiltonian as terms of normal complex fermions. So what Kitaev did was to rewrite this with our new definition of gammas. So if you write the F's with gammas, you will end up with a Hamiltonian like this. So yeah, it will look like this, and we end up with I because of the definition actually. These two are the same Hamiltonian, represented in different ways. So let's talk about these Majorana zero modes inside our Kitaev chain, which are frequently talked about. So the thing is, Kitaev argued that in his chain, in his toy model, you can actually pair up the Majorana modes, the Majorana fermions, either like the normally like this, as you have seen in the last slide, normally like this, like gamma 1, gamma 2, gamma 3, gamma 4. By pairing up, I mean like consider two of them as a normal complex fermion, and you can actually change the pairing, and by changing the pairing you will end up with two dangling unpaired Majorana modes at the end of your chain. So what Kitaev argues is that by having certain parameters, by changing the parameters of our system, you will end up with this excited state called Majorana zero modes for a finite size of your system. And as you increase the size of your system, this state actually goes down and down and down and approaches the ground state. And for an infinite chain, you will end up having two unpaired Majorana modes at the end of your chain, which are called these Majorana zero modes. And the word zero stands for zero energy. For zero energy, it's in some sense an excited state with zero energy, but yeah, for infinite chain, you will end up with a doubly degenerate ground state. But as you increase the L, as you can see, the Majorana zero mode approaches the ground state exponentially. But the thing is, in real world, we always have a finite chain. We can have a very long chain, but not an infinite chain. So in reality, it's always Majorana almost zero mode. But the thing is that this energy gap decreases exponentially, and we're hoping to see these Majorana zero modes as an excited state of our system. Experimental difficulties. One of them is that it is harder to, the superconductor, it is very hard to have superconductivity in one dimension. As you know, it doesn't work very well in one dimension, and what we do is we put the system in proximity of the nanowire. So we have a nanowire, we put it in the proximity of the superconductor, and it will induce superconductivity in this nanowire. But there comes a lot of more problems in here. So if you wanna go one step further from the toy model of Kitaev to the real world, we need many more stuff like spin orbiting coupling. We need a magnetic field. And one of the problems with doing this in a laboratory is that we actually need a super homogeneous, very neat, as you say, kind of system with controllable parameters. We should be able to control all the parameters of our Hamiltonians. So in real world, instead of having that toy model, we'll end up with another similar Hamiltonian, which in here we have J, mu, alpha, v, z, and delta. With J is hopping, as you can see, it's the hopping between two terms plus the Hermitian to conjugate. Mu is the chemical potential. It is calculated with respect to J. This is the onside term. Alpha is the spin orbit coupling. As you can see, so these are spin orbit coupling. This is the Zeeman splitting, and Vz is the external parameter of our system, and the delta is the same Cooper pairing. So that's superconducting Cooper pairing, external field, spin orbiting coupling, and the normal hopping and on-site terms. So yeah, that would be the experimental Hamiltonian that we are going to work with. And yeah, so what we're going to do is we're going to use non-equilibrium green function to calculate the IV characteristic of our nanowire. And we can see that this is useful to find our Majorana zero modes, and to find that these zero energy excited states in our system. So you might have heard of non-equilibrium green function, and before going on, I would like to quickly go through this non-equilibrium green function. And so this NEGF is actually the same green function that we covered inside the course, but it is the state for non-equilibrium states. So the physics of non-equilibrium is a very rich and yet not very fully known physics that a lot of people struggle to know better. And the thing is, in non-equilibrium green function, all expression from equilibrium green function theory remains valid within the non-equilibrium theory by simple replacement of time integral with a contour integral. So yeah, basically whatever you know from green function will stay the same for non-equilibrium green function, except the integral of your time. Instead, we're going to do a contour integral. So what do I mean by that? Let's have a simple explanation so we can understand it. So, in here we have an expectation value of some operator, as you can see in non-equilibrium state, you can write it as some trace over row of that operator, and this row is called statistical operator, defined like that. And as you can see, as you know, this is the Heisenberg operator, and these are the time evolution operators of our time independent operator O. And as you can see, these operators U takes you from the time t0 to t, acts the operator O on it, and then take you back to time t0 from the time t. So yeah, so this time evolution actually, as the name suggests, they evolve the time from some time to another. So a non-equilibrium and time-dependent expectation value. So remember, that's a time-dependent representation, which is the Heisenberg representation, and that's the non-equilibrium expectation value. So if you combine them, we'd end up with something like that. And in here we did something smart, which was to write this like that, and you can actually check that these are the statistical operators the same. So instead of having normal time in here, we replace it with minus I beta, and yeah, and if we replace it upstairs, we'll end up with something like that. So the expectation value of some operator is the trace of U, which takes you from time t0 to t, acting O on it, takes you from time t to time t0 again, and then from time t0 to time t0 minus I beta. So you can see we're moving in a plane, in a weird way in time plane. So you can actually think of it as some sort of contour in the complex time plane. So we are all familiar with the real time and the imaginary time. Now imagine you have the whole complex plane of time with both real and imaginary parts, and imagine having this contour of having this pass inside the complex fermion, inside the complex time plane, instead of having a simple integral. So yeah, we're replacing this with this. And what we're saying is to get the trace by the, now instead of having this time ordering operator, we're having this contour ordering operator. So these two are actually equivalent ways of saying the same thing. So yeah, that's the actual idea behind the non-equilibrium green function. And that is that instead of having the time ordering and moving only in the real part or imaginary part for zero temperature or not, we're moving inside the plane on a contour and the operators are actually should be, instead of having a time ordering parameter, we're now having a contour ordering, which orders the terms based on the order they appear on the contour. So yeah, that's how we treat the non-equilibrium green function, and this is very important to get the transport properties of systems. So back to our system. So we have a S-wave superconductor, as I said, and a nanowire on it, right? And we expect some Majorana zero modes happening here and here if the length is sufficiently long, right? And this was our Hamiltonian, as I've discussed. So what people do is we're going to do some transport calculations, some IV diagram of our system, and because there are zero modes, we expect some peak over zero bias voltage. So what we do is we connect some left electrode or left lead to the left side of our system and some right electrode or right lead to the right side of our system, and we create this voltage between them, and we actually want to calculate the current between these two normal metals actually, and we use NEGF to calculate this. Actually, NEGF is a very, very famous way to calculate the transport properties of different systems, and yeah, and you probably will end up using it somehow, or actually hear it at least, if you're working in this matter, probably. And so and we expect, as I've said, a peak at the zero energy because of the Majorana zero modes. And so yeah, before continuing, there's this number spinors defined like this as a four spinors of Cx spin up. So this is actually the normal complex Fermion creation with spin up, spin down. This creation annihilation of different spins, and if you put the four of them, you will end up in these so-called number spinors. These are very well used in systems with superconductor, and that's the way to write things more compactly. This is a good thing to introduce beforehand. And the actual green function will look something like that. This is the green function that we're all familiar with. The only difference is that this is not a time ordering, because we're not dealing with the equilibrium green function, but it is a time, and non-equilibrium green function is more general form, and because we're in superconductor, we're actually dealing with these number spinors, which is just a way to write it more compactly and more nicely. And yeah, and actually from that, by calculating the green function, we can actually calculate the current between two sides from the time-dependent one-particle reduced density matrix, which is actually defined like that. And if we do the calculation, we'll end up with this from our Hamiltonian, which I've defined in the last slide. So yeah, using an NEGF, we can calculate the I, or or actually the differential conductance between the two leads, depending on the voltage of the two leads, left and right lead. And you can actually see that if we increase the number of sides, you can actually see that there will be a zero energy peak, and this zero bias peak is believed to be the Majorana zero modes that we're looking for inside the real experimental world. So of course this is a numeric calculation, but what we know is that based on this green function calculation, we expect that if we go ahead and create this system and get the current and the voltage between the two leads, we should see this peak on the zero modes. And if we see that, we're seeing actually Majorana zero modes, and we're seeing two pair of Majoranas at the end of the chain. And as you can see, for small chains you can't see actually the Majorana zero modes, because it is basically for a sufficiently long chain. So as a conclusion, we've learned about Majoranas as a real and imaginary part of a normal complex fermions, and we've learned what are Majorana operators, what do they look like, and how we can create them, and actually how we can see them and we can exploit them in real physical world using Kiddive chain. And then we talked about how we can see them in an actual laboratory outside of the world of the theory, and we've learned that we can actually use NEGF, non-equilibrium green function, to calculate the conductance properties of that Kiddive chain, and to have some point that we can somehow infer from it that these Majorana zero modes do actually exist. And here are some other points that I've pointed out, that even though Majorana particles have not been found in nature, must emerge in the condensed matter physics, and the non-equilibrium green function, or NEGF method, which is widely used for calculation of transport properties of same systems, can be used to check for the existence of Majorana zero modes. The thing is that normal impurities do also create this kind of peak in zero bias state, and one has to be careful to distinguish these Majorana zero modes from these normal impurities, and we can actually have to somehow distinguish these two, and we should actually show that these are in fact Majorana zero modes and not normal impurities, if we're going to do it in normal experiment. By the way, people have done it, and some people believe they found it, some people think there's still more work to do, and so yeah, these are very interesting topics and things to know, and but still there are many current research that has been going on using NEGF methods, and people are actually engineering a more simpler and more controllable systems with Majorana zero modes, because as I've said, the system should be neatly homogeneous, and parameters should be all controlled in this model based on the toy model of KitIve. But what people are doing right now, as like these months and these years, as I'm talking, is that what if we don't care about the KitIve model chain, but we actually change the model itself and the geometry itself, or the parameter itself? What other kind of systems are there? So with the same kind of properties, with Majorana zero modes inside them, and and all of these things are also doing a green function and non-equilibrium green function to calculate. And the references, and thank you for listening.